So hello everyone. So first, a few announcements. So last session I promised to do a short game at the mid time each day, but in fact I prefer to spare more time for the course because I have so many things to tell you about. So sorry for the enigmas, and maybe I keep them because they're really interesting. I keep them for coffee breaks or whatever. So this course is much more work than I expected first, because as I told you last time, I'm not following a textbook. I really present my vision of physics, of quantum foundation, but in fact of all physics, and that's great. I love it. It's a lot of work, but I must say I love it. It's scientifically super rich for me, and I love it because I can really be creative and create some original perspective on the topic. And broadcast a message about physics and the avenues for what is interesting for the future of quantum foundations and even QFT, quantum gravity, and so on. So it's a great experience, and that's why really a big thank to Serge Lazarini and Thierry Masson for having invited me to give this course, because I realize now, maybe I didn't realize so much in the beginning, but today I realize how a great opportunity it is for me. I'm not talking about the CV only. I'm really talking about scientific and artistic production. So thank you to both of you, Thierry and Serge, and also thank you to you present today, because on Sunday it's my birthday, and I must say it's possibly the best birthday present I could have. Namely having people from the LIS and from the CPT both gathered in the same room to listen to the same course. I love, helping creating bridge between communities or gathering different people. And there are no philosophers as far as I know here, but maybe just because there are no philosophers here on the campus, but it would be even greater to have, mathematicians, physicists, philosophers, quantum information theorists, and so on. But it's a big success for this reason so far. So thank you. And let's go. So I finished chapter 1 that we started last time. I had just 2 little ending sections, and then it's very exciting because it's the chapter about the measurement problem. So one of my favorite topics, very close to my heart. So again, for the people who were not here last time, feel free to raise your hand at any time. I love when it's interactive. So we have plenty of time. So yeah, feel free to ask questions and react. Good. So remember, the last section was we finished with some no communication theorem and some philosophical remarks about the tensor product structure and so on. And if you remember, look at the summary. The section 2, just after introducing Dirac's notation, was entitled Computing Probabilities PVM Presentation. And PVM, remember, a PVM is just a complete set of orthonormal projectors forming a resolution of the identity, but perfect projectors. And now we will introduce the concept of PVM, a central concept in quantum information. But I will give a few philosophical remarks which I take from Fuchs. So I read this paper. I recommend this paper. Look at the title. So it made me think twice. Until a few months ago, PVM for me, I didn't like so much the concept. It was just not a fundamental concept at all. But you will see. I want to share an idea with you coming from this paper from Fuchs, which I find very interesting. So what is a PVM first? Suppose you have a joint system, joint quantum system. So suppose initially non-entangled, so you have a rho 1 pure tensor, rho 2, non-entangled, but it's not. Yeah, you can always suppose that it's not. No big loss of generality. Evolves. So evolves. Joint evolution, and so of course you, as we saw last time, you conjugate by the corresponding unitary operator for the evolution. Good. And then what do? you and then a measurement, but a PVM measurement, so the canonical way we defined the measurement earlier, so a perfect projector. A PVM measurement is performed on row 2, on the system 2 only. PVM so PVM measurement corresponding to a set of projectors. So corresponding, so I can just name them. To the projectors. So last time, remember, we said when it's a question on the second system only, I put the identity on the first Hilbert space and a projector, orthonormal projector, on the second, right? So remember, we discussed philosophically the grounds for doing this, but this is the standard way. Good. And now you can use the Born rule, and we'll compute the probability of obtaining. So we defined it last time. PVM is projection valued measure. Big K. So you because you have a PVM we define it as a resolution of the identity in terms of orthogonal projectors. So sum of pi k over k. K is an index. It's just a family. It can, so you cannot have more index k than the dimension of the Hilbert space on the 2. Yeah, but it's a resolution of identity in terms of projectors. And we said that when you do a measurement on a system 2 only, but within a Hilbert space of a joint system 1 and 2, we said the corresponding projectors are identity here and the projector here. And we no, here it's identity 1 just to specify. No, it's because it's the family, so k within a range of indices here. I just specified the family and not one projector. Good. And now I can use the Born rule. So using the Born rule, the probability of obtaining k after this PVM measurement is, so we showed that this is the most general formula. You just take the trace of the state multiplied by the corresponding projector. Okay? This is the Born rule. Trace of rho pi. So it's good, but let's rewrite this expression. So let's specify some basis of H1 and H2. I should write, yeah. B, basis. Remember, when I say basis, implicitly it's always orthonormal basis. In quantum mechanics, we literally never use anything else than orthonormal basis. So implicitly, think of orthonormal basis of H1 and H2. We can rewrite the Born rule this way. So P of k. So it's a trace, right? So it's a trace. So I sum over everything. It doesn't depend on the particular choice of basis, as you know. So by cyclicity of the trace, I can move the unitary on the other side. Okay, I just write the trace and move the unitary. Yes, thank you. Yes, right, thank you. And now, so this, well, let me write it this way first. Maybe we find the expression a little bit weird at first, but I will explain it. Sum over j. So I try to separate the indices I and j. So what is it? Here, you have to understand this in the bracket as an operator. This is in fact what we called last time trace over 2 of identity or 2 trace over 2 of the thing inside here. U dagger. Because remember we showed, or maybe I didn't show it, but I wrote it down. This is the general formula for actual computations of the trace, the partial trace of something. You know, remember? So this is an operator in H1, right? Here, yeah, here. Okay? Think of it as an operator which has been partial traced on the second. And now, so how can I write this? This is true because, remember, I also showed, or maybe I didn't show it again, but I claimed the formula because, remember of last time, trace of ρ1, 2, A1 tensor identity 2 equals trace of the partial trace of ρ1, 2, A1. This is the fundamental property of the partial trace, which we use here, and we showed it last time. And now I can say this is trace of ρ1 ek, where ek has been defined as this. So no big mystery again. U dagger. Right. Okay. And it's really nice because now we started from the Born rule, but on a tensor space. And so the expression is, it's not ugly, but it's a bit complicated, right? And now we were able to rewrite it as something that looks like the Born rule on just H1. So I have a system of interest S1. I couple it with another one. I do a measurement, projective measurement on the second one, and everything happens, and I get an outcome, K. And the probabilities can be computed of obtaining outcome K, can be computed only from the knowledge of ρ1 plus this strange object Ek, using the normal Born rule, right? And we could show as well that the state that you recover after measurement can be obtained only also by using the Ek. So what does this mean? So we can show that this we can. I will explain what are the properties that satisfy this object ek, or this family of objects ek. And if you understand, we are doing quite the same thing that we've been doing already maybe a couple of times, meaning do something on one system and try to generalize on a pair of systems and find the most general mathematical object that implements this. We did it for unitary evolution, which yielded CPTP maps, and we did it for already for the pure states, which yielded the density matrices. But here, so what are the properties of the EK? The EK, the family EK, is a family of positive Hermitian operators that, just like the PDM, that forms a resolution of the identity. Resolution. So positive means, you know it, but just to be sure, for all psi, psi ek psi, I should say non-negative, but we don't say non-negative operator. So as far as I know, we don't say that. Yes, H1, yeah. Exactly. And resolution of the identity means sum over EK equals identity 1. All right. Now definition. Any family satisfying these properties is called a POVM. So POVM means positive operator valued measure, because the k here it's discrete. So imagine for all k you give a positive and imagine that k lives on a measurable space. You can build a kind of measure, but positive operator valued and not projector valued. That was the PVM. Positive operator valued measure. POVM. Crucial ingredient of quantum information theory. Note that there is no restriction on the number of indices k, because the number of the indices k is the dimension of H2, but you can couple H1 to anything a priori. So there is no restriction on the number of indices k, contrary to the PVM case. Of course, because the PVM, at most, in finite dimension, at most you can have n orthonormal projectors in a space. No, it's not obvious. One can show, yeah. I should write, one can show I guess it's not so hard. I mean, I didn't even. I'm not even sure I checked the proof once. Now remember when I introduced the notion of CPTP maps, we did the same. We tried to do something general, restrict to one Hilbert space, show that, oh look, the evolution is, we called it a CPTP map or a channel, and we said, oh look, this channel psi satisfies this and this and this property. One can show that. And then I said, conversely, Stein-Spring theorem says that any object satisfying this property is in fact obtained by coupling a quantum system to a bigger one and restricting the unitary. Here it's the same. So here it's not Stein-Spring, it's 𝗰𝗵𝗽𝗁 dilation theorem. Conversely, 𝗰𝗵𝗽𝗁 yeah, is it the 𝗰𝗵𝗽 from non-commutative geometry? Probably. I'm not sure. 𝗰𝗵𝗽 dilation theorem states that any POVM can be obtained how do I formulate it, as a PVM, as above, as a PVM performed on S1 plus we call that an ancilla system. I don't know, maybe it's not extremely clear how I formulate it, but I guess you got my points. In a larger space, yeah. In a larger space, H1 and so H2. So this is for the POVM. But why do I introduce this? Because first I will need it on the chapter for the quantum to classical transition at some point. But I really want to do some interesting philosophical remark from Fuchs. First table, summarizing table. So standard measurement. PVM, generalized measurement POVM. So just to recap, you have, what do you have here? A family PI of orthonormal projectors, so such that for all psi pi I is non-negative. Sum of the pi I is the identity. You have the Born rule. P of I is just trace of rho pi I. And you have the orthogonality condition, which you can write this way. Right, they are projectors, so the square is themselves, and orthogonal, so product is 0. Yeah, so they are Hermitian. So because this is not even defined if they are not Hermitian. Yeah, Hermitian. Yeah, yeah. Project. Yeah, but projectors is here. Yeah. Yeah, at least. Yeah. So maybe Hermitian. Hermitian. Yeah. Yeah. No, but yeah, it's always the same. You know, when you give a course, people are doing interesting comments, and either you take 2 minutes to write down the idea, but you lose some time, or you don't, and then you forget. But I decided to take this time for POVM. Hermitian as well. What do you have? For all psi is non-negative, all right? You have sum of the k, ek is the identity. Now you start wondering why am I writing all this? And here you have nothing. So which one do you prefer? Do you prefer PVM or POVMs? Well, who cares, right? It's the same, all right? Yeah. Why not POVM? It seems simpler, right? so most people, I mean, I don't know if most people, but I didn't like POVMs up to, a few months ago before reading this paper by Fuchs. Why? Because I thought, no, but this is fundamental. And this is just an artifact when, in fact, you do a PVM on a larger system, and this is just an artifact, you just rearrange the math. But what happens, the true measurement in the universe is this, right? I thought that. And then I thought twice, thanks to Fuchs, because, let me explain. Is the POVM, is the PVM really more fundamental than the POVM? More fundamental, and the POVM just an artifact derived from it. So is it true? So what do I mean? I mean that when we remember the very first section, I said quantum mechanics is a geometrical way of computing probabilities, and I said events are subspaces, so identified to orthogonal projectors. I said physical state are vectors, etc., etc. But I could have said also, no. On the first day, I could have said, no. It's a probabilistic way. It's a geometrical way of computing probabilities in which events are elements of POVMs. I could have said so, right? And I could have given the Born rule. I could have given this, and you would never have wondered about all that. So, is there an argument for deciding this question, the last question I wrote? Of course, it's really a kind of philosophical question. There's no definite answer. But just some remark. So POVMs can be seen as families, as complete families of what I call fuzzy projectors. Because they are Hermitian, so they are diagonalizable in some basis. And the only difference is that a pi A is diagonalizable with eigenvalue 1 or 0. 1, and then 0, 0, 0 in some basis. Right? This is so this is very sharp. I select super sharply a subspace in my Hilbert space. Whereas this, I don't know how to write it, but it sums, it can be anything between 0 and 1. So I don't know, I don't have a proper notation, and then you can have zeros. But here, anything in 0, 1. So So these are fuzzy projectors as opposed to sharp projectors. Okay, you can see it. So the question is why should we think that fuzzy projectors could be more fundamental than sharp ones, or is it the converse? So I just for now again a question perhaps. Fuzzy measurement, fuzzy projectors, fuzzy questions should be seen as primary object. Of the quantum mechanical framework. So again, remember, I could have, on the first day, I could have presented from the start the notion of P of M without ever talking about PVM and say, this is the fundamental way we ask questions in quantum mechanics. We could have done that. Here is the last section. So, last section of this chapter, presenting a wonderful, widely acclaimed theorem in quantum foundation, Glisson's theorem, which will, so it's very interesting in itself, but it will serve as a justification or a clue for perhaps answering this question. So what is this Glisson's theorem? So remember, I am very in love of the Born rule. It's wonderful. You cannot imagine a more refined and elegant and pure way of building a geometrical probabilities to compute geometrical theory for computing probabilities, as I argue. But despite its elegance, can we motivate even more the Born rule? In fact, the latter has a property of universality. It is the only way to compute probabilities in a Hilbert space, with a lot of quotation mark. But I will. This is the message of Glisson's theorem: universality, or maybe canonicity. Here's why. So here's the theorem. Yeah. Theorem by Glisson. In the 60s, I think. I don't, yeah. 60s probably. So let H be a Hilbert space. Of dimension larger than 3. I think it's finite dimension all the time, as always. I'm not even sure. Do someone know if Glisson's theorem is true in infinite dimension over that? No. And let P be the set of orthogonal projector in H. Set of pi such that pi is orthogonal projector in H. Set of projectors, but sharp projectors. Suppose there exists a function f from P to real number in 0, 1, such that sum of the f pi I is 1 for all complete set of projectors pi I, complete family of projectors pi I. Then this is wonderful. There exists something rho in S of H. So S of H is, remember, it's the set of positive, Hermitian positive trace 1 operators in H, such that f of pi I of pi equals trace of rho pi for all pi. This is incredible, just incredible. And this theorem is super hard to show. So let me explain. So many remarks. Can you see something? Yeah. Many remarks first. Let's spend a little bit of time on this. Remarks. So the theorem gives not only the Born rule, but also the state space S of H. Because S of H, remember, we built it from, consideration of partial traces and so on, and Stein-Spring theorem and so on. And we said, in fact, the good object encoding every predictions for one single system is a rho living in S of H. But here we have it for free without any consideration of last time. We know that this is a good state space, and we know that the probability rule, that the Born rule appears naturally. Theorem derives not only the Born rule, but also the state space S of H. Now, what do the theorem means? So you take a Hilbert space. Why? So you consider the set P. So P is the set of questions that you can ask to your system. So the PVM question, the standard measurements. And so what is this function f? Suppose, so you want to say, okay, my questions are the PVMs. And if I want to build probabilities or attach probabilities to my questions, I should be able to build a function associating to any question a probability. And the only thing we suppose on f is this. We want that it sums to 1, but of course it's a probability. And we want that, and for any complete set of measurement. So it's very general. Yeah, you just say my PAVMs are the good questions. I want a probability on it. I should have that. There is one hidden, or yeah, it's not hidden, but it's very clear. But there's one assumption behind this. It's what quantum physicists would like to call a non-contextuality assumption, or something like this. because we want to say, okay, the probability of a PI does not depend on the rest of the complete set I choose. So I can choose, for example, 2 orthonormal bases having one vector in common. They should have the same probability, whatever the rest is measured, right? So the fact that f of pi depends only on the projector, which is the subspace, the event, the probabilistic depends only on the projector, could be called a weak non-contextuality assumption. So non-contextuality means, well, super hard to explain. It's like there are books and billions of pages written about that. It's super hard. It's a super hard field of research, contextuality. But here it's a very weak, very simple way. Just the idea is, I should attach probabilities to every event, no matter the context of my measurement, no matter what I measure in fact. So no matter the complete set of projectors that I actually measure, every event has a probability in itself. Okay. Now, more interesting, and this is the reason why I wanted to show this theorem. This theorem is extremely hard to prove. And I have never seen the proof, I must say. But if you do the same, but now if you consider that the fundamental questions, probabilistic elements, are not the PVMs, but the POVMs, then the proof is very natural. It's not trivial, but it's very natural. The proof, is very fluid. It's not super long. You understand what happens in the proof. And also it holds for all n, not only from dimension 3. Right, and this is for Fuchs, and I like the observation. It's not an argument, but it's a clue of maybe PVM should be deemed fundamental, maybe more fundamental than POVMs, or at least it's an interesting observation. So, but if one rather considers that POVMs are fundamental, the theorem for P replaced by P prime set of set of EK, where EK is a POVM, something like that, become, so of course you assume more because PVMs are a particular case of POVM. So now if you want the property to the assumption to hold for every POVM, of course you assume more. So you intuitively know that the proof should be easier, but still it's interesting to see that how beautiful and elegant the proof is. I don't have time to show it today, but we could do it in the course. It's not so hard. So becomes reasonably easy to show very natural proof, and it holds for all dimensions. It holds also for dimension 2. So the question I want to ask is, yeah. Sorry, no. So the eigenvalues are it's it would be the what I showed earlier. It's just the table I just erased. It's just trace of rho ek, the Born rule for the P of EMs, which is the same. Remember, the Born rule is unchanged. It's just the table I was just erased before. So if you look at it again, the Born rule is the same. So, concluding remark of this chapter and transition for the following chapter. So again, a question, I can never state anything firmly when discussing these topics, but should we take seriously in the formalism that perceptions are always fuzzy? I will develop this a lot more in the coming chapters and maybe in all the rest of the course. But I think it's very in line with maybe the lesson of quantum mechanics, right? That we live in a world of finite resource, right? So in fact, using real numbers is always a fiction, right? Always infinite precision is always a fiction. And when you do physics, when you write a number, in fact, you don't have a number. You have a strange mathematical object which should be modeled as something with error bars. You know, this is what you do in physics, and and the use of real numbers in physics works to the extent that we have in our labs super big measurement apparatus, super finely tuned to extract exactly what you wish, and you pretend that that actually there is a value and you could build more and more accurate measurement apparatuses. In fact, no. In fact, you don't. And there are some fundamental limit to the precision of measurements, and we live in a finite world. So we have to take this seriously, the fact that we live, even physicists are constrained by finite resource. So perhaps POVMs really grasp something very deep. I'm not sure. I just wanted to show this because I changed my mind very recently, as I told you already. And because I'm using more and more the notion of POVMs in my daily work, especially in the context of the quantum to classical transition, because there are reasons to believe, this will be the last chapter, that classical physics is just the fuzzy limit of quantum physics. You take quantum mechanics, you acknowledge that you live in a finite resource world, and you recover classical physics. So this is a teasing for the very last section, but now, first the measurement problem. Chapter 2. Measurement problem. And let's start with a little history. This is a timeline. And the timeline starts in the 1870s. What happened in the 1870s? It's the advent of statistical mechanics. Jerry, correct me if I say some historical imprecisions. It's fuzzy. Yeah. Do you have a better date? So, no. What do you have before statistical mechanics? Well, you have in physics, I mean, you have full knowledge. There are no probabilities, so you know everything that happens in your physical system. The second date, so what do you have afterwards? Well, you have what I like to call epistemic ignorance. So now you have probabilities, but I mean, they just denote the fact that you ignore something, but it's still there. It exists, of course. Then there is, so this date is also very controversial. 1909, for me, it's a landmark in humans' history. What happened in 1909? If anyone guesses, really, I offer you a beer or whatever you wish. But it's very unlikely that you guess, because I had to check the date for this course. I didn't even know it before. I was looking for a date where the first quantum interference experiment was performed. The first time that we know that humans experimentally observed something very weird at the level of the statistics that we will explore in this chapter. So the first, of course, Jung did some optic double-slit experiment, classical ones, and in fact it's already quantum, because the reason why, well, I'm going to come back on this, but and in 1909 a guy called Taylor tried to limit the intensity of the source doing a Jung double-slit experiment, and realized an experiment in 3 months, so 3 months exposition of the source, but so tiny source that, in fact, if you do computation today, you can compute that on average there was only one single photon at a time. So it was the first double-slit experiment, quantum double-slit experiment, where we noticed that even photon by photon behaves super weirdly at the level of the statistics, the experimental statistics. So Taylor's first double-slit experiment with single photons.
Was there a reason he was doing that, or just there was
Well, it was it was fashionable at this time to try to do experiment on single particles. No. That's it. So I'm not sure he was even aware of the huge experiment he was doing. And it's a good question. I don't know the motivation. Yeah. So what? Yeah. So it was not clear. That's why 1909, just to have a date, and I will say a few more things about that. But it was the first time where, I mean, he just had a source and then a lot of filters, and he had a 3 months exposition. And if you do computation of the filters he used, on average, there is only one photon at a time that passes through the experiment. But okay, it's not. I mean, yeah. Just to have a date. In fact, already in 1905, if you take Einstein and Planck's work, it's already enough, because Einstein and Planck works had already shown the discreteness of light. And I mean, yeah, and then you don't have, yeah, you still don't have the experimental input of what happens when you do one single photon, but you have the classical Young experiments, and you can reasonably think that, you know, photons they don't interact a priori on the experiment, but probably this experiment is the real landmark. And then you can also use 𝗬𝗪, but it's 20 years afterwards or something, 15, 20. 𝗬𝗪 is not an interference experiment, but still you can look at the, yeah. For me, it's less conclusive than this on what I'm going to explain afterwards on the weirdness of the statistics, but still, if you use 𝗬𝗪, it's well explained in Pierre's book. You can already see that something weird is happening, because if you know the spin had values on all directions, it shouldn't behave this way. But for me, this is the real landmark. So good. So what happened after Taylor's experiment? Well, I want to say, and you will understand. Maybe I wrote it afterwards. 1926. What happened in 1926? Maybe people here in the room know. You said equations? No, Schrödinger equation, proton 5, I think. But for me, for my purpose, Born's paper, which gave the name to the Born rule. Born's paper, but at the time it was what the real intuition was the probabilistic interpretation of the wave function. Probabilistic interpretation of psi. So very interesting, because now we are, you know, people knew or started to see that quantum mechanics is in essence a probabilistic theory, but not of the same kind as this one, but it was not yet recognized. 1935, two things, and I think you might know that. So two things in 1935, Schrödinger's cat, Schrödinger's cat paper, and the 𝗵𝗺𝗽𝗺 paper. So tremendous year. Schrödinger's cat, you know, 𝗵𝗺𝗽𝗺, Einstein, Podolsky, Rosen, and it's the thing that Bell was replying to. 1952. Incredible year, because David Bohm proposed Bohmian mechanics. Yeah, so it was de Broglie. So I was expecting this reaction. Have you read de Broglie's work? You did? Yeah. So thank you, because I didn't. So what was it really like everything already present? Yeah, no, but de Broglie's work. So something here. Was it already containing Bohmian mechanics in itself, or was it just like tiny premises of the idea? Was it fully developed? But I mean, it was already presented as a theory shown to give the same prediction as quantum mechanics, with the interpretation of particle with definite position and trajectories and so on, with all the ontology coming behind. Yeah, that's why I think Bohm did the job, and I think, as far as I know, de Broglie just did a little mathematical trick to rearrange the equation, but I'm ready to, I don't know, I'm not a historian. Bohmian mechanics. For people who don't know what is Bohmian mechanics, if I have time, there is at the end of the chapter we review the 6 main interpretations, and Bohmian mechanics is one of them, but I'm afraid I won't have time. But if you really want to know, just come to me and ask after. I'm here for 3 more weeks. 1961. Thierry, do you know this one? Wigner's friend. Wigner wrote a paper entitled On the Mind-Body Problem in 1961. Well, it was Wigner, so of course people read it and commented it a bit, but not that much. Because when you see today, literally every day, you have plenty of papers appearing on Wigner's friend, and we are presently finding so many theorems and remarks on the depth of this thought experiment we understand only today. So 60 years after Wigner, how deep it was and how it was really capturing one of the biggest, one of the essence of the measurement problem. 1964, this one you know it for sure, because this is Bell's theorem. 1982. Yeah. Aspect experiment. And what happens here? We change era. I still didn't say what was it. Now we live in the era of ontic ignorance. And ontic, as opposed to epistemic, ontological if you want it. Here it was ontic ignorance, but not recognized. In fact, it's not very well recognized still today. Ontic ignorance. So something different from just purely epistemic ignorance. Probabilities denote something more. It's not just there is a state of affair and you don't know. No, there is something different. And this is what I will argue in this chapter. And crazily, I was looking for something. Yeah, sorry, 1992 is also something, yeah, another thing. Another great year for the measurement problem. Zurek seminal paper on decoherence. And so during the following 30, 40 years, the decoherence research program was pursued quite successfully. And so here I could name like just many papers about decoherence important, but I mean, yeah, this is the important year, the start of the research program. And crazily, I was not able to find another important date up to 2020. Yeah, a question, yeah. This is the purpose of the chapter, to explain it, of course. Yeah. This is the local friendliness theorem. Friendliness theorem. So I guess most people in the room don't know what it is, but chapter 3 will tell you more about. But you will have to wait because not in this chapter. It's surprising. I was not able to find a. Maybe I will disappoint, or maybe even I don't want to disappoint or be rude or forget anyone, but there is a big hole here. Maybe I'm forgetting something. So standard presentations. of the measurement problem. How do experts today define the measurement problem? MP. Well, it's a mess. There is no consensus. No one agrees. No clear formulation on which everyone can agree on. It's a mess. On which everyone can agree. Sorry. And it's a community quite violent. The debates in the paper, that's okay, but in the debates, when you really talk with real persons in conferences and so on, everyone is defending their school, their interpretation and their solution. Everyone thinking otherwise is deemed stupid, and the debate just do not progress, because I mean people, Heisenberg, Bohr, Einstein, and so on, Pauli, they were obsessed by this. And then Second World War and second half of the 20th century, almost nothing. Well, you have dates, but Bell, he was an alternative. No one read his paper. And Wigner, there was Wigner, quite an exception. Aspect, he had so many troubles to just get funding, and so. And here there is a gap, and it's a bit weird, because in fact it's reviving since the 2000s, and thanks to quantum information probably, because much more fundings for the field, and also thanks to probably to the decline of string theory and the failure of the different attempts to quantum gravity, giving much more room to other new or not new, sometimes very ancient approaches to physics. Why am I saying this? Yeah, a quote by Feynman. (1982). He said, "I cannot define the measurement problem. Therefore, I suspect that there is no real problem." But I'm not sure there's no real problem. Typical Feynman sentence. So it doesn't say much, but it gives you a taste of what's the, what's the attitude towards the measurement problem. When you do a literature search to try to see how do people define the measurement problem, which I did recently, you find, I propose roughly 3 categories. But it's really my proposal, and really, again, it's a mess, so it's super hard to build categories or anything. Roughly 3 categories. For most of the literature. Category 1, first proposal. The people who say there is no real problem, or it is trivially, or it is solved by decoherence. Second proposal, the people who say the problem is the fact that only one outcome occurs in a quantum measurement, or people who just say there is a mystery. The problem is that to explain that any outcome at all occur, something like that. So the problem is that only one outcome occurs in a quantum measurement. So this is, for example, Carlson, Wiseman. This is a personal communication because I like to ask in conference, go to experts and ask this question: what's the measurement problem for you? He's really an expert, and he's one of the author of the local friendliness theorem. I respect a lot his work, but he replied in this category. Yeah, and he replied this in 2024. Maybe he changed his mind. I don't know. Or any outcome at all. This is, for example, Saunders. Simon Saunders, a great philosopher, great name of the many words interpretation. Or Adlam, probably my favorite philosophers of physics, but on this, I must say she disappointed me a bit. But sorry, Emily. So what's the intuition behind? I want to explain to show that, yeah, what make people think that. Intuition behind. So you can find it in many textbooks. Suppose you have, so what am I writing here? When we discuss the measurement problem, we don't care about the normalization of the vectors because we just write up plus down and you divide by square root of 2, but I mean we have more important to do. Okay, no normalization. This is a spin, a qubit superposed in up and down. And this lives in the Hilbert space of the measurement apparatus. And this is a state where my measurement apparatus is in a ready state, ready to measure, right? So, yeah. Measurement apparatus. Qubits, spin 1/2, whatever. During a measurement, it evolves into this. Up becomes coupled to the apparatus recording up and displaying up on the screen. Plus same thing with down. And you get into a superposition of up and down coupled between the spin and the apparatus. Checking the time. Oh. But you could extend. Could be extended to up plus down, apparatus ready, and this is physicist ready, and it evolves to up, apparatus up, physicist. Oh, I have seen up, plus same thing with down. Okay. Well, I will write it because I have seen down. Yes, but me, when I do it, well, I am not an experimentalist, but when my friends experimentalists in Vienna do that, well, they leave only one outcome, right? They experience one and only one and not zero and not several. So the formalism seems at odds with this, right? but the physicist sees exactly one outcome, or only one outcome. So to ensure this, the pioneers of quantum theory added the famous collapse. And they say, oh, if I see up, I collapse my state so that it's compatible with what I really experience. So to ensure this, textbook quantum mechanics adds the famous collapse of the quantum state. But then the problem is, when do the collapse take place? Because what's the difference between a measurement apparatus and a physicist? Is it because there is a conscious human being experimenting and therefore the collapse is linked to consciousness and so on? And where to place the Heisenberg cuts? This is, maybe you've heard of this expression, the Heisenberg cut. So the pioneers of quantum mechanics were struggling with that. Where's the border between classical and quantum world, if there is one? Well, it seems that there is one because of this problem and because of the collapse. So originally, the Copenhagen interpretation was based on an idea of a radical, and it's still true today, radical border between a classical world and a quantum world, and there is a domain of validity of quantum mechanics. Quantum mechanics can be applied to anything, but not to everything at the same time, because there should be a classical world. This is an important tenet of Copenhagen interpretation, but I'm coming to this. Third proposal. The people who say, this is the most frequent definition of the measurement problem you can find in the literature. It's super hard to find something else, in fact. The problem is the conflict between unitary evolution and the collapse. So unitary evolution means it's linear. It's Schrödinger equation. It's linear and deterministic. Deterministic at the level of the probabilities. It's a meta-determinism, but the equation is deterministic at least. And the collapse is famously nonlinear and stochastic. Okay, this is advocated by many people. So first, von Neumann, 1932. Remember the textbook that influenced all quantum mechanics still today. So you find this idea of where to place the Heisenberg cut and where to place the collapse and so on. He had an argument to show that it doesn't matter, you can place it anywhere yet still, but there are many problems coming after that. Everett was motivated, when proposing the many worlds interpretation, was motivated by the measurement problem, and the way he defined it was exactly this, copied from von Neumann. More recently, a famous philosopher, famous in the domain, in the community, but 𝗬𝗫𝗺𝗫𝗺, so already more than 10 years ago, but also 𝗬𝗫𝗺𝗫𝗺, Hervé 𝗬𝗫𝗺, I think he's in Belgium, important name as well of the measurement problem. Probably you know better Gisin. probably you know, no, maybe you don't know Barrett, but important name, also philosopher, advocate of the many word interpretation, and plenty of others. So the thing is, you have two apparently conflicting postulates in the textbook's formulation of the postulates of quantum mechanics. Mind that I didn't present quantum mechanics in terms of 6 postulates. I hate this presentation. You can't imagine how much, but the textbook is this way, and so there is apparently two conflicting postulates, and there is apparently no recipe that tells you which one to apply in which case. So no recipe tells you when to apply one or the other postulate. So I hate this. It's painful for me to write that, but postulate of quantum mechanics. Okay, this is the third proposal. After, we'll have a fourth and a fifth one by two people who did something much more original, which I love. But first, I want to reply to this and explain why it cannot be a definition of the measurement problem. So, but these definitions cannot be satisfactory. So for the first, I don't even want to, lose my energy replying to these people. I think, like, at the end of the chapter, if it's not clear that decoherence doesn't solve the problem, I don't know what to do. So the rest of the chapter will hopefully show that this stance is naive. Is naive. So let's not lose too much time. But second, this is important to reply because so many people, quite many people saw that. So for me, quantum mechanics is a probabilistic theory. So, and just like statistical mechanics, no one has never questioned the fact that when you do probabilities, you have several potentialities and you observe only one. Of course, I mean, no one has never questioned that. If tomorrow you go to a lab and you observe two outcomes, then this will be the big mystery to explain, right? It will be a much bigger mystery than the measurement problem already is. If you observe two outcomes one day, just tell me, and you will see how the tremendous revolution in physics it will generate, and people will forget about the measurement problem probably. So, how to write this? Quantum mechanics is a probabilistic theory. Of course, it involves a variety of potentiality. And of course, there is only one observed. Observed of course. How could be otherwise? So again, if someday you observe two outcomes, much bigger mystery. Now let's reply to the third proposal. It's too rooted in the textbook presentation of quantum mechanics, and especially in von Neumann's presentation, because again, everyone copied von Neumann for this. But if you take, I mean, there are 6 main interpretations of quantum mechanics, as we will see. In 4 out of 6 of these interpretations, there is not even a notion of collapse. So it's not even meaningful to say that. For a Bohmian advocate, the person would just say, what are you talking about? I don't have a collapse. If you take to a QBist, they would say, what the fuck? If you take this to a many world, precisely they don't have a collapse because the wave function is just develops all the time. And for relational quantum mechanics, the same. So it's not an interpretation independent formulation. It's the way the measurement problem manifests itself within the Copenhagen, and I should say it's not really Copenhagen because true Copenhagen advocates are much smarter than this, and it's the mainstream textbook way, slightly influenced by the historical primacy of the Copenhagen interpretation and by von Neumann, and that's all. So it's not a universal definition of the problem. So too rooted in the textbook, especially von Neumann. Von Neumann's presentation of quantum mechanics cannot be no, not interpretation independent. Can't be a universal definition. Had physicists first developed quantum mechanics in terms of Bohmian mechanics, they would never have come out with this formulation of the problem. Physicists first developed quantum mechanics, or historically developed quantum mechanics in terms of, say, Bohmian mechanics, but it works for many other. And it could work also for formulation of quantum mechanics that we still haven't found today. Bohmian mechanics. We would never have defined the problem this way. On 4 out of 6 interpretations do not even have a collapse. So no. Yeah, we will at the end of this chapter we will study them. If I have time, probably not, in fact, but only Neo-Copenhagen or Neo-Copenhagen and collapse models have a notion of collapse. For the first one, it's mainly epistemic. For the second, it's ontic, objective, physical process. But for the others, no, there is not even a collapse. Yeah, I don't have time to write this, but that's important. Besides, yeah, I should write this. Besides, in any probability theory, think of statistical mechanics. When you acquire new knowledge, of course you update your probability measure. Suppose I have it doesn't happen in statistical mechanics because in essence, we are not supposed to measure just one particle. In essence, we do averages. But if you did it, and if you were able to measure, the position of one particle in your gas of particle, you will know more, and you would update your probability measure to have more accurate prediction, right, for the future. So when you acquire some, and it's the case for, I'm just giving physics example, but just think of any probabilistic theory. You acquire new knowledge, you update your probabilities, and this is the collapse. This is nothing more. And of course there is a collapse. And Bruckner wrote in 2017 on a paper called On the Quantum Measurement Problem. He divided the measurement problem into the small and the big one, and the small is clearly presented as not a problem. And he said, not only quantum mechanics, but every probabilistic theory in which probabilities are taken to be irreducible must have the small measurement problem, namely the presence of a collapse. The lack of the small measurement problem in probabilities theory would contradict the very idea of having irreducible probabilities. So the collapse, besides the collapse is a very natural operation in all probability theory. Acquiring new knowledge yields an update of your proba measure. This is the collapse. In quantum mechanics, we call it the collapse, and we say it's super mysterious. And it is because there is a very particular property of quantum mechanics, because it's not a normal probabilistic theory. We will see why. But the presence of a collapse is not in itself a problem. This is the collapse. Right. So, fourth proposal, very interesting. Maybe I don't do it. Okay, I would just, I will do something. Fourth, now we go, so from the least interesting to the most interesting proposal. 𝗦𝘂𝗺𝗿, Tim 𝗦𝘂𝗺𝗿, great philosopher of physics, 1995, proposed an original way to define the problem, and he was trying to be interpretation independent. Proposed original attempt. The measurement problem is the fact that these three assertions are incompatible. One, psi is complete, meaning that psi so it specifies all there is to know about a system, all properties of a system. Two, psi evolves according to Schrödinger equation. Three, measurements have definite outcomes. So at the end of the measurement, the device is either in a state indicating, for example, up and not in psi, or down and not down. So measurements have don't write. So yeah, a measurement apparatus at the end of measurement is either in states up or in states down, or not a combination thereof. And so I wanted to show you the argument why this is incompatible. It's quite easy, but yeah, you can have a look at the paper. And in fact, this is the first set of assertion he proposes, and then he proposes two other sets, a little bit more refined. My comment, so interesting approach. But three things. Three reasons why I'm not happy. First, although he criticizes it, the formulation still relies on the ill-defined notion of measurement, which he criticizes in the very paper. So still, Bruckner defined the measurement problem as the big measurement problem as what makes a measurement a measurement. I must say I don't like so much this formulation because it's too vague, and again it's too rooted in the Copenhagen way of formulating the problem, but in a smarter way than this one. But still, for the Copenhagen, the problem is to define this word. So if you try to define the measurement problem with this ill-defined notion, of course it's hard to think you have made any progress. Second, it's not a positive definition of the problem, meaning you don't really know what's wrong with quantum mechanics. You know you have to reject one of these three, but first which one? And then you are left with a feeling of not really, grasping what happened. So not a positive. Yes. No. Objective collapse models have not been confirmed experimentally, and in fact, they are desperately looking for confirmation. But the set of possible parameters is decreasing more and more and more. It's becoming harder and harder to believe in this. And for now, no experimental physicists have found any deviation from Schrödinger equation. No one has been. It's impossible in today's technology to show that, because you should be able to perform a measurement, and then your apparatus or the physicist experiencing the measurement, you should be able to build an interference experiment on the physicists themselves, which we cannot do today in present technology, and we probably never be able to do that. So no one has been able to show a deviation from Schrödinger equation. And the collapse in the Copenhagen interpretation is mainly understood as an epistemic process, an update of the probabilities, as I was explaining before, but not a physical process. And only the collapse model advocates think it is a physical process. It's an interesting avenue to pursue, but if you think that it's extremely constrained, the math, you have almost no choice. There are only two possible models, in fact. Experimentally, it's becoming harder and harder to believe it, because there are experiments currently done, and also it cannot be compatible with special relativity, which is a little bit of a problem. But we have a well, you can ask, because probably we will not have time to see each interpretation one by one. So yeah, feel free to ask questions. But yeah, not a positive. You understand what I mean? You still left with a feeling of what happens. What's the problem? Which one should I reject? Third, proposed before RQM, so relational quantum mechanics, RQM. So which appeared in 1996. And the newborn, the youngest interpretation, QBism, 2002. So no wonder that if 𝗬𝗺 was doing that today, he would probably adapt the argument quite a lot. Okay. Fifth, but still, I mean, I criticize, but I love it much more than the previous one. And fifth proposal, I think for now today existing in the literature, it's the I forgot to say something. For me, it's the smartest proposal for now. Wallace, fantastic philosopher of physics. It's always a pleasure to read his papers, although I disagree quite often. Defines. So I don't have time to explain the full paper. It's super long, but just in a nutshell, in one sentence, hiding everything. But sorry, you can please check that if you're interested. The problem as the conflict between the interpretation of psi or rho as either a space, quote, a space, or a of the quantum state space. As either, quote, a space of physical states which I kind of did in the very first section of this lecture, where I said, you know, physical states are vectors in a Hilbert space. So Hilbert space is the state of quantum states, a space of physical states, or as a space of probability distribution. Which I did as well, because I said, no, psi is just a tool to compute probabilities. This is what quantum mechanics is about, a geometrical way to compute probabilities. And there is this tension of giving too much ontology to psi and saying, no, it's the state of the system, whereas in fact it's a state of probabilities. But there's this tension because the outcomes of measurements are supposed to be eigenvectors of Hermitian operators, and we give them, you know, physical classical interpretation of, yeah, my system is exactly in this state, right? I'm sure you have plenty of things to say, and I'm sure you're not convinced by this, because it's impossible to summarize this paper in one sentence. So I apologize, but just to advertise this proposal, because I like it a lot. And now let's take inspiration from this proposal, but make the idea more compelling and clearer. Let's try to do that. Section 3. So this section is mostly based follows, so little advertisement for a forthcoming paper, forthcoming which I have presented quite a lot of time in conferences, and Emily accepted to collaborate with me on this project. I'm super happy because I love working with her, and so you can find my slides or anything in. I've presented it quite a lot of time in conferences, and I'm very surprised because I propose an interpretation independent formulation, and I'm surprised by how easily people are convinced that it is a good formulation, and how I receive agreement from people from like super different schools. As I told you before, communication is hard between, and my hope in the long term is to be able to improve the communication within the community, without having everyone, saying that the others are stupid, and finding a common point from which to discuss, to start in the debates. So, how can we be interpretation independent? To be let's do like Bell theorem will be valid even though even if in 1 year quantum mechanics is superseded by another great new theory. Bell theorem will be exactly untouched, unchanged. Why? Because it deals only with the statistics, the empirical statistics. Bell theorem is a theory-independent theorem, just like other theorem that I will present in the following chapter. So let's formulate the problem purely in terms of the empirical statistics. Oh, as a property. Yes, purely as a property of the empirical statistics. Like Bell. So Bell's strategy. I'm not quite sure at that time Bell, in 1964, Bell was aware that he was creating a new strategy, but it's now widely acknowledged that this is how we do theory-independent things. This way, thus, the argument would survive even if quantum mechanics is superseded by a new theory. Right. So at some point, I remember someone told me, yeah, but we should stop deriving philosophical consequences of physical theories, because we had classical physics and then relativity entered the game, and so everything every conclusion that we could have before have collapsed, and everything is changed, and the worldview is changed. But no, I don't agree. There are things that are theory independent and that will resist in time. Now, remember the punchline that I've written down at least a couple of times and said a billion of times already. Quantum mechanics is a geometrical way of computing probabilities, but I promised to expand this punchline later in the course. So today we have the full punchline. Quantum mechanics is a geometrical way. Sorry, I let the suspense. So is a geo way of computing proba in which which does not satisfy the 𝗂𝗺𝗃𝗺𝗃 axiom of probability theory. Kolmogorov axioms. So what are the Kolmogorov axioms? A probable measure is, you know, a map from a measurable set, blah blah blah, normalized to one, having sigma additivity property. And is there anything else? I don't know. I don't think so. There is another one? No, no. Okay. Especially the sigma additivity property. And more precisely, because normalization you have it. So more precisely, it doesn't satisfy the sigma additivity or equivalently what I call the total probability formula. There are plenty of ways to call that total probability formula, TPF, which is just a trivial consequence of the sigma additivity. P is obtained by conditioning on the value of something else. This is the TPF. So some people call it the sum rule, or the sum rule or the law of total probability or whatever. But I prefer to call it a TPF because it is neither a rule nor a law. It's just a trivial consequence of sigma additivity. Yes, it's time? All right, thank you. Thank you. Didn't we start 5 minutes later? Okay. It's so follows from sigma additivity because P A equal A is just P of, you know, the set union of, and by sigma additivity they are disjoint. So and then by definition of the conditional probability, okay, trivial consequence of sigma additivity. But I prefer to emphasize this, and you will understand why, because it has, I think, some philosophical. It's the translation of a metaphysical assumption. So the TPF is not satisfied by for quantum systems. So I must acknowledge here the paper which have been so influential to me when I was doing my PhD. Stable Fact, Relative Facts by Andrea and Carlo. So emphasizing the importance of the TPF, and for me it was a landmark. An example, stupid example, double slit experiment, right? The probability of obtaining the electron at some point on the screen is not the sum of the probability given it was on the right plus the sum given it was on the left, weighted by the corresponding probabilities. And in fact, any interference experiment is a deviation from this, as I will argue now. General reason. In terms of the Born rule, let's check that you don't have the TPF in quantum mechanics. Trace of rho XX. So this is a one-dimensional projector. I could take more general, but it wouldn't help understanding anything more. So yeah. where ij are some orthonormal basis of my Hilbert space, and so it can decompose rho ij this way, right? And then I separate between the diagonal and non-diagonal elements. And here I have a real part of some weird stuff. Right. And I claim this is a TPF because this is, so this is the probability of obtaining I. This is the probability of obtaining I given X. And this is what we call the quantum interferences. Namely a deviation from the TPF. This is the general reason why the TPF is violated in quantum mechanics, so no big mystery in terms of math, but very big mystery in terms of philosophy. So yeah, I will stop at 5. Can I have 5 more minutes? Thank you. Okay. 2 definitions. What is coherence? Quantum coherence. So it's very fashionable at the moment to try to talk about coherence coherence, because it's the main resource used by quantum computers to do computation that allows to do something that classical stuff cannot. So coherence in a basis B is the ability to deviate from the TPF at the level of the statistic, the empirical statistic. This is coherence. And decoherence is the process after which the TPF is approximately satisfied when conditioning, should have written that here, but decoherence in B when conditioning on the potentialities of B. So decoherence is a process, coherence is a quality. Okay? Process after which, so meaning it is the after which rho becomes approximately diagonal in B, because the diagonal elements are account for the TPF, and the non-diagonal ones account for the deviation. So in 2 minutes, very, very crucial moment of the course. What does the TPF means? Consider, so what did Bell do and the other Nogov theorem? They have metaphysical assumptions that you can write down in words and say in sentences, and then they translate it into math, into properties of the statistics. And then they say, if all of them are satisfied, we have a contradiction because such a proper measure should satisfy a bound, an inequality, a theorem, whatever. And they show that empirically, the bound is violated. So one of the metaphysical assumptions, which are independently not untestable, become testable together. Here we do something much simpler because we have only one metaphysical assumption, which I translate into the TPF. But claim, no, consider the metaphysical O. So O, even though the actual value of a variable is not known, it still has a definite value among the possible ones, which I can rephrase. There is only epistemic ignorance. So for now, I just state it as a as a metaphysical statement on the world. I'm not yet translating it into math, but in fact, your question is very relevant because the very definition of a hidden variable. First, it's hard to find a universal definition, but if you look at Bell's first formulation and most formulation, in fact, they are translated in terms of a TPF. And I will come to this later. So I wouldn't say TPF implies hidden variable, but for sure, hidden variables rely on a TPF. Because they want to capture this notion O. O means, I take it for objectivity. But the use of this word is very controversial. So main claim of this chapter, claim the TPF is the mathematical translation of O. And I think I stop here for today, but just orally, more precisely, an observable B could be deemed objective or satisfying O if for all A, the TPF holds for the probabilities of A when I condition on B, meaning that I know nothing about B, but it is objective. It has, a definite value. There is only epistemic ignorance, so and when I compute the probabilities of something else, because B has a value, I can just sum all the possible histories. They don't see each other. They don't interfere. If I repeat the experiment, I just weight every branches, every potentiality by the potentiality of the branch. And so just one example that I give all the time in conferences. Suppose I give an exam to my student. I don't know whether my student has worked or not, but I know that she has either worked or not. And so the probabilities that my student gets a good mark at my exam is just the sum of the probabilities that she has a good mark given she has worked times probability she has worked plus the same thing with hasn't worked. And this implicitly means that my student has an objective state, an objective property, which is having worked or not, which is I can ignore, but it's epistemic ignorance. And yeah, so for next time, no. So I can define the measurement problem. So just one sentence. Empirically, we detect a violation of the TPF. Therefore, O must be rejected this is the measurement problem I claim. And next time we will develop the philosophical consequence and try to restate this in terms of philosophical words, not just math. Thank you for your attention for today.